Welcome to chapter 27 on the wave nature of light. So we've said in earlier videos that light has both a wave and particle nature. Prior to this, we talked about light traveling in a straight line in our geometric optics. So now we're going to look at light acting like a wave rather than a particle moving in a straight line. One of the first people to propose that light might actually have wave properties was Huygens. He was a Dutch contemporary of Newton's, and he's the one who proposed a wave theory of light. In his theory, he viewed light as being comprised of lots of little wave fronts that come out, and each little part of the wave front acts like a new source for the light. So he says in his principle, Huygens principle, it says that every point on a wave front can be considered to be a source of tiny waves that spread out in the forward direction. So if we pretend in this diagram from the textbook that this line represents our wave front, and it's got 3 points along it. Each one acts as a source for a new little bit of wave moving forward. So we have these little arcs. If you want to think of waves as a circular shape or an arc shape, think of a raindrop hitting a puddle and how the ever widening ring spreads out. Well, that's sort of what we're looking at here. So the waves come out, and there are so many of them, and they're so close together that they overlap, and we get the second wave front as it moves forward. And then each point on that acts as another one. And so the wave just moves out and it gets larger and larger. And again, think of what happens to the little ripples that a raindrop will set up if it hits a puddle of water, how it starts out small and just expands as it moves out. So with Huygens' principle, we use it to explain what happens when light undergoes diffraction. Diffraction is the bending of a wave around an obstacle. You may think of, suppose you've got a crack in a door and your room is dark, but there's a light on in the hallway. Well, light enters the room, but it enters it in sort of a pie shape. It's narrow right at the door, but into the room itself, it expands out and gets larger. This is due to diffraction, to the bending of the light around the little slit that the crack in the door makes up. You can see this with water waves. This is a photograph that we have. So here you have a wall with an opening in it, and we have a water wave that started. When the water wave hits the little opening, instead of being just a nice long wave, you see that you get these little arc shapes as the wave itself bends around the opening, and they get ever and ever larger as it moves out in a forward direction. So the wave is moving in this photograph from left to right. Yep, I'm going the right direction. All right, so here's a line drawing of the same photograph. The incoming wave comes in, it hits the obstacle, and we get this arc coming out. This diagram, figure 27.9, is from your textbook. What's important about it is for you to notice that if the opening is really large, then the outgoing wave looks a lot like the incoming wave. There's very little curve to it. But if you narrow the opening, if you make the opening smaller, the outgoing wave begins to curve. And in fact, the smaller it is, the more curve you get to it. So changing the width of the opening can change the shape of the outgoing wave. Diffraction is possible only for waves, not particles. Particles, when they hit an obstacle, do not bend around it and make these little arc shapes. Grimaldi was a monk who showed that the diffraction of light was possible by using a hole in a window shade. Unfortunately, Newton was very popular at the time, and he believed in a particle theory of light and couldn't quite grasp that maybe light could act like two different things. And so it took years for a wave theory to be accepted because Newton was more influential than Grimaldi or Huygens. One thing we should notice is that diffraction is only possible when the size of your obstacle or hole is on the order of the size of the wavelength. So they have to be roughly the same size. So we're going to talk a little bit about Young's double slit experiment. You will actually do a version of this in lab. Thomas Young demonstrated the wave nature of light with his double slit interference experiment. He was able to take and split a beam of light into two beams and then let the beams come back together. And what you would normally expect would be just two bright spots, but that's not what he got. Instead of two bright spots, he got a series of bright spots separated by dark bands. We call these fringes. And they indicate that the light has undergone an interference pattern, that some of the light has added to produce bright spots and some has canceled out to produce dark spots. So we have a series of bright and dark spots. When they're in phase, we get bright spots. When they're out of phase, we get dark spots. So you will see this in lab. We will have both a red and a green laser. So in the center of our pattern will always be the brightest spot. That is something called the central maxima. The central maxima is in the middle. And then on either side of that, you'll see a dark region. That's the first order minima. So the maximas are bright spots, the minimas are dark spots. So central maxima in the center, first order minima on either side. Just to the right and to the left of that first order minima, you will have the first order maxima. So it will have another series of bright spots. So central bright spot for the central maxima, first order minima on either side, first order maxima after that. Then we move on to second order minima, so a dark spot. And then we'd have second order maxima on either side, and then you'd have third order minima and third order maxima, and it just keeps going out farther and farther. Depending on the brightness of the laser that you use and the darkness of the room, sometimes you can see quite a few of these patterns, and sometimes you're lucky to get one or two. So again, we'll need to be able to locate the central maxima, the first order maxima, and the first order minima, as well as second order minima and second order maxima. You need to know how the counting goes in this. Our setup in lab, we'll have a double slit. That's what these little boxes represent with the light coming. The laser's over here on the far left-hand side. It hits the double slits, and so part of the laser beam comes up and part of the laser beam comes through the second slit, and it will bend as it moves through the slits and produce bright and dark patterns. What is completely unexpected, of course, is that we're going to get a bright pattern in the very center. We'll get a bright pattern in the very center, and then there'll be a dark on either side and a light on either side of that, and the pattern will continue, alternating bright and dark spots. So we were able to come up with an equation for this. You'll notice that the distance between one slit and the other slit is symbolized by little d. That's our slit separation. The distance between the double slit and the viewing screen is capital L. So this total distance is capital L. And then in the pattern itself, the distance between the central bright spot and wherever we're looking at is X. That's our separation distance between the very middle of the pattern where the central maxima is and whatever place you want to ask your question of. So how far away is X from the central bright spot? Well, we have a formula for that. X is equal to little m times lambda times L divided by D. Little m is called the order number, and we'll talk about that in just a minute. Lambda is the wavelength of the light. Capital L is, again, that separation distance between the slit and the viewing screen. And little d is the slit separation. All of your distances have to be measured in the same units, so either all in meters or all in centimeters or all in millimeters. And since we have three things measured in distance, lambda, L, and D, they all three have to be in the same units. And little m is the order, and what that tells us is which of those bright or dark spots are we looking at. So for the maxima, remember those are the bright spots. If m is 0, we're looking at the one in the very middle. And since that's where we're measuring from, X would be 0. If m is 1, you're looking at the first order maxima. So that's the bright spot to the right or to the left of the very central one. If m is 2, that's the second order maxima. And so you would be looking at the bright spot 2 places to the right or the left of the one in the very middle, and so on. Now, for those dark spots, for the minimas, m has a value of 1/2 if you're looking at the first order minima. So it's that first grouping of dark spots either to the right or the left of the bright spot in the middle. First order minima, m is 1/2. Second order minima, m is 3/2. So the second grouping of dark spots, m is 3/2. For the third order minima, it would be 5/2, and then so on. You have to be able, if I tell you we're looking at the first order minima or the second order maxima, you have to be able to decide what is m. So light's thought of as having a dual nature. In some experiments, it's going to act like a wave. In others, it's going to act like a particle. We will utilize this equation in the lab on Young's double slit, and I'll probably do one calculation with it in class. All right, let's look at the visible spectrum and dispersion. Dispersion is what gives us all kinds of pretty effects. Rainbows are a result of dispersion. I guess that's probably the one that we're most familiar with. So when you disperse white light, you spread it out into its full spectrum, red, orange, yellow, green, blue, and violet. So prisms and water droplets and diamonds and leaded glass all do this way. They work because of the index of refraction is really a function of the wavelength of the light. So every color actually moves through a transparent material at a slightly different speed and spreads out at a slightly different angle. The shorter your wavelength, so violet is short and red is long, the larger your index of refraction. And the closer to the normal your colored light's going to be bent or refracted. We could use Snell's law to actually calculate it. We're not going to. But we could and actually figure out if the white light comes in, knowing the index of refraction for each of the individual colors, we could figure out the dispersion angle for each of the individual colors. We won't, but we could. All right, let's talk for just a second about thin films. So a thin film is a soap bubble, or it's the skim of oil that you sometimes see in parking lots where you get this sort of rainbow effect. And there are other places we see thin films. Sometimes they're on the glass in your automobile to sort of help shield the interior of the car from sunlight. So sometimes light gets out of phase. It shifts a little bit when a single beam will split as it reflects off the top and the bottom of a surface. So when this happens, you have the opportunity to take white light and turn it into colors. And like I said, we see this most often with soap bubbles or oil slicks. So in the little drawing, the light comes in, some of it reflects off the top surface, some of it comes down and hits the bottom surface and reflects up. And your eye sees both of these. They're going to be slightly out of phase with each other, so there'll be some constructive or destructive interference depending on the thickness of the soap film. And that will control actually the color of the light that you get. So the colors are really dependent on the thickness of the soap bubble or the thickness of the oil slick, if that's what we're looking at. So all these pretty colors, the turquoise or the hot pink of course is the magenta, those colors are controlled by the thickness of the bubble, the thickness of the film. We're not going to do the math. I'm presenting the equations for you in case you're curious about it. We have other things to do. So if we want to see a bright color, the light has to undergo constructive interference at that particular wavelength. For destructive interference, we need a different set of criteria. So one of the places we use this, besides explaining the colors in a soap bubble or the colors in an oil slick, is to produce non-reflective coating. Some of you may wear glasses and have spent a little extra money to get a non-reflective coating on your eyeglasses. If that is the case, what's happening is just some of the rays are being absorbed so that you don't get the glare bouncing off of it. And it's a bit of proprietary information. They apply different layers on the outside of the glass in order to do this. You also see it in some glass used in picture frames. If you have a photo, a picture that you want to hang in a room that gets a lot of direct sunlight, you might spend money to have that. And that finishes our chapter. So we will stop the video